Welcome to the deep dive. Today, we're tackling quantum computing. It's one of those topics, right? Sounds like science fiction, super complex.
Absolutely. It definitely has that mystique.
Hmm.
But it's becoming, well, more real every day.
Exactly. So our mission today is really to unpack it, try and break it down. So if you're new to this, you can, get the main ideas, what it might do, and maybe what it means for the future.
That's the plan. And yeah, at its core, a quantum computer, it's not just a faster version of your laptop. It's fundamentally different.
Different how?
Well, it uses quantum mechanics, the physics of really, really tiny stuff, particles,
Right, the weird physics.
the weird counterintuitive physics, yeah. And it uses that to do certain calculations, potentially exponentially faster than any normal computer could.
Exponentially faster. Okay.
Yeah, we're talking about solving problems that are just impossible today, even for supercomputers.
So let's start with that difference, the basics. Classical computers, the ones we all use.
Right, they run on bits.
Bits, zeros and ones, simple. On or off, that's everything. Your phone, apps, the internet.
Everything, it's all binary logic.
Sure.
Process things one after another, or maybe in parallel, but still, it's zeros and ones.
But quantum computing, it throws that out the window, starts with something else.
It really does. The
Yeah.
basic unit is different. It's not a bit, it's a qubit, quantum bit.
Qubit, okay. And what makes a qubit so different from a bit?
This is where it gets interesting. A bit is either 0 or 1. That's it. A qubit.
Yeah.
Well, it can be 0, it can be 1, or, and this is the key part, it can be both 0 and 1 at the exact same time.
Both, simultaneously. How does that even work?
It's a core quantum concept called superposition. It's like, well, it's not just a faster bit. It's a whole new way information can exist.
So instead of definite states, it's more like possibilities.
Exactly. Probabilities and connections between them. It lets quantum computers use these weird quantum effects, superposition, entanglement, interference, to get incredible speedups for certain tasks.
Okay, superposition. That sounds like where the real, the magic is, if you can call it that. Can we dig into that a bit more? How can something be two things at once?
Yeah, it bends your brain a bit, doesn't it? Think of it like a coin spinning in the air.
Okay.
Before it lands, is it heads or tails?
Well, neither yet. Or both, kind of.
Exactly. It's in a superposition of heads and tails. A qubit is similar until you measure it. It can be in a combination of both 0 and 1.
And that's powerful because...
Because it scales incredibly.
Yeah.
If you have, say, n qubits, they can represent 2 to the power of n states all at once.
Whoa. So, like, 3 qubits isn't 3 bits of info. It's 2 times 2.8 states at the same time.
Precisely. It means the computer can explore a vast number of possibilities simultaneously. Not one by one like a classical computer, but all at once.
Mind-boggling. Okay, so that's superposition. Then you mentioned entanglement. That sounds even more mysterious.
It is pretty strange. Einstein famously called it spooky action at a distance.
Spooky action. Why?
Because when you entangle two qubits, their fates become linked, no matter how far apart they are across a room or across the galaxy. Theoretically,
Linked how?
their states are correlated. If you measure one entangled qubit and find it's a 0, you instantly know the state of the other one must be, say, 1, or whatever the linked state is. Instantly.
Instantly. Faster than light.
It doesn't transmit information faster than light. That's a common misconception. But the correlation is instantaneous. It's like they're one single system, even when separated.
And this helps the computation.
Hugely. It creates these powerful correlations that quantum algorithms rely on. It allows parts of the computer to work together in ways classical bits just can't. Essential for the speedup.
Okay, so we have qubits being 0 and 1 at once, exploring tons of options and linked together through entanglement. How does it find the right answer in all that possibility?
That's where quantum interference comes in.
Interference, like sound waves or water waves canceling each other out.
Exactly like that. Quantum states also behave like waves, with amplitudes and phases. During a calculation, the quantum computer is designed so that the paths leading to the wrong answers interfere destructively. They cancel each other out.
And the path to the right answer?
That one gets constructive interference. It gets amplified. So the probability of measuring the correct answer increases, while the probability of incorrect answers shrinks. It's a way of sifting through the possibilities.
So you're guiding the quantum waves towards the solution. But eventually you need a normal answer, right? A 0 or a 1.
You do. And that's the final step,
Oh.
measurement.
And what happens then? All the quantum weirdness just stops.
Pretty much. When you measure a qubit that's in superposition, it collapses. It's forced to choose. It becomes definitively 0 or 1. The quantum state is gone, and you get a classical result.
But if it's probabilistic, you might get the wrong answer sometimes.
You might. That's why the goal is to design the calculation, so the correct answer has a very, very high probability of being the result when you measure. And often, you have to run the calculation many times.
Ah, okay. Run it again and again to be sure.
Exactly, to build up statistical confidence that the answer you're seeing most often is the right one.
Got it. So, putting it all together, how does a quantum computation actually run, step by step?
Well, first you need to set things up. You initialize your qubits, usually putting them all in the zero state, like clearing the register.
Okay, start fresh.
Then you apply quantum gates. These are the operations, like logic gates in a classical computer, but they manipulate the quantum states.
Gates, like rotations, you mentioned that.
Yeah, you can think of them as rotations on a sphere representing the qubit state. They carefully nudge the probabilities, create superposition, entangle qubits according to your algorithm.
So you're programming the interference pattern in a way.
That's a good way to think about it. You run the qubits through a sequence of these gates, which we call a quantum circuit.
And then?
Then measurement. You measure the final state of the qubits to get your answer. And like we said, probably repeat the whole thing multiple times for accuracy.
It sounds incredibly delicate. What are these qubits actually made of? You mentioned extreme conditions.
They are incredibly delicate. That's a huge challenge. And yeah, the hardware varies. A lot of the big players, like IBM and Google, use superconducting circuits.
Superconducting, like zero resistance.
Exactly. But to get that, you need insane cold, temperatures close to absolute zero, colder than outer space.
Wow, why so cold?
To stop heat and vibrations, any environmental noise from messing up the fragile quantum states. Keep them coherent.
Are there other ways? That sounds difficult to manage.
Oh yeah, there are several approaches. Another big one is trapped ions. Companies like IonQ use this.
Trapped ions, like single atoms.
Yep. They trap individual charged atoms using electromagnetic fields, then zap them precisely with lasers to control their quantum states.
Are they better in some ways?
They tend to be very stable. Their quantum states last longer, which is great, but scaling them up can be tricky.
Any others?
Sure. There's photonic quantum computing using particles of light, photons as qubits. Xanadu and Sequantum are working on this. The nice thing there is photons aren't as sensitive to temperature.
So maybe easier to build?
Eventually, yeah.
Yeah.
Though controlling photons precisely has its own challenges. And then there's Microsoft's approach, which is more theoretical right now, topological qubits.
Topological. What's that?
The idea is to encode the quantum information in the shape or topology of the system, making it inherently much more resistant to errors from noise. It's kind of a holy grail, but still very much in development.
Okay, so fascinating tech, different ways to build them. But what can they do? Is this going to make my video games run faster?
Huh. No, afraid not. Quantum computers aren't going to replace your everyday computer for things like gaming or web browsing or writing documents.
So not general purpose.
Definitely not. They are highly specialized machines. Think of them more like accelerators or coprocessors.
Yeah.
For very specific types of problems where classical computers just hit a brick wall because the problem gets too complex too fast.
Okay, so what kind of problems are they good for? Where do they shine?
Well, the most famous example, maybe infamous, is breaking encryption.
Right, you mentioned that. Shor's algorithm.
Exactly. Shor's algorithm lets a quantum computer factor large numbers incredibly quickly. And the security of a lot of current encryption, like RSA used in banking and secure websites, relies on the fact that factoring is super hard for classical computers.
So a powerful quantum computer could break it.
Potentially, yes. Crack RSA encryption in hours, or maybe even seconds, something that would take a classical computer billions of years. That's a huge deal.
Definitely. What else?
Simulating quantum systems themselves, which makes sense, right? Use quantum to simulate quantum.
Like molecules.
Precisely.
Yeah.
Simulating molecules for drug discovery, designing new materials for batteries or catalysts.
Yeah.
Chemistry is fundamentally quantum mechanical, so simulating it accurately is incredibly hard classically, but potentially quite natural for a quantum computer.
That could be revolutionary for medicine and materials science.
Absolutely. Also, complex optimization problems. Finding the best solution out of a huge number of possibilities. Think logistics, financial modeling, maybe training certain types of AI models more efficiently.
And machine learning, too.
Yeah, there's a growing field looking at quantum machine learning, solving certain complex linear algebra problems that pop up in AI, potentially much faster.
So, focusing back on that encryption thing, it sounds like a double-edged sword.
It absolutely is. The threat to current encryption is real, and it's why governments and companies worldwide are urgently working on post-quantum cryptography.
New codes that quantum computers can't break.
That's the idea. New encryption methods based on mathematical problems thought to be hard for both classical and quantum computers. It's a critical transition we need to make.
But can quantum computers also help with security?
Yes, they can.
Hmm.
There are things like quantum key distribution, or QKD, which uses quantum principles to create theoretically unhackable communication channels. So it's a race, really. Quantum breaking codes and quantum making new, more secure ones.
Fascinating. But it sounds like we're not quite there yet. What are the big hurdles? Why don't we have these powerful machines everywhere?
Oh, the challenges are immense. Number one is errors. Qubits are unbelievably fragile.
Fragile how?
Any tiny bit of noise, a stray magnetic field, a slight temperature change, even cosmic rays can knock them out of their quantum state and cause errors in the calculation. This is called decoherence.
Decoherence. They just lose their quantumness.
Pretty quickly, yeah.
Yeah.
We're talking microseconds or milliseconds for many types of qubits. Keeping them stable long enough to do complex calculations is really hard.
So you need error correction.
Massive amounts of it. The idea is to use many physical qubits, maybe thousands, just to create one stable, reliable, logical qubit that can compute reliably. That's a huge overhead.
Which leads to the next problem, I guess. Scaling up.
Exactly. Scalability.
Mm.
Current machines might have, tens, maybe pushing 100 or so usable qubits, but the algorithms for things like breaking RSA or complex simulations, they might need thousands, perhaps millions, of high-quality interconnected logical qubits.
Millions. We're a long way off.
We are. Building these large-scale fault-tolerant machines is probably the biggest engineering challenge of the century so far. And of course, they are incredibly expensive to build and operate right now.
Makes sense. So, despite the challenges, who are the main companies pushing this forward? You mentioned a few.
Yeah, there are quite a few players now, big and small. You've got the tech giants like IBM, heavily invested in superconducting qubits, and they even offer cloud access.
So people can try them out.
Yeah, researchers, businesses can run experiments on IBM's quantum hardware through the cloud. Google is another major one, also with superconducting tech. They claimed quantum supremacy back in 2019 with their Sycamore chip.
Supremacy meaning?
Meaning their quantum computer performed a specific, carefully chosen task far faster than even the most powerful classical supercomputer could. It was a milestone, though debated.
Okay. Who else?
Microsoft is in the game, pursuing those topological qubits and offering their Azure Quantum platform, which connects to various hardware types. Then you have IonQ, focusing on trapped ions, known for high-quality qubits. Rigetti is another significant player with superconducting chips and cloud access, often focusing on hybrid quantum classical approaches, and many others, startups, university labs. It's a bustling field.
Sounds like a real race.